There are two things about this probabilistic method. Of course, it became one of the major tools in combinatorics, and it has books and great applications. Two developments out of it. One, that it started being refined, and you mentioned before, I think, the semi-random method. So maybe you can give an example of what this is.
Actually, this is very strange that we developed this, let's call it now method, though for a very long time they didn't call it a method. It was just buried in a obscure paper, not obscure journal, but obscure paper. It was a journal, European Journal of Combinatorics. And then actually what we wanted to construct a dense infinite Sidon sequence. For a long time it was an open problem. Still there is no complete solution, but at least that was the first step.
So a Sidon sequence is a set which does not contain any of the differences.
Right, so any
elements.
two differences of is different. Yes, that is a Sidon sequence, and then up to n how many you can have. Always it is easy to prove. Then if you just randomly choose an n to the 1/3 you have. But whether you can have more, of course, you cannot have more than n to the 1/2, because then just by the volume argument, or I don't know which one, or principle, whatever, it's easy to prove. But n to the 1/3 was for a very long time, for 40 years, the best.
N to the 1/3 means there are, if you pick randomly n to the 1/3 integers between 1 and n, no difference will be
right,
contained.
And then you can continue it up, so it will, the whole problem is for infinite, because for finite and there were a construction, then square root an element, but this is just a finite set. But the problem was an infinite, and then of course there is an interplay between the elements, and then we constructed where for every n we had at least n to the 1/3 times log n elements. And for that we needed this, let's call it lemma, which by our opinion, but this is only our opinion, started the so-called pseudo-random method, that to run theorem states the following, that you have a graph on n vertices, so that the maximum degree is d, then you have always an independent set of size n over d. And of course you cannot improve it, because you have a common union of complete graphs on the vertices, then this is it. Every degree is d, and then of course from every complete graph you can choose only one point. But then we started to meditate what is the reason why to run theorem is such as, and then we realized if the number of triangles, not that much, but a little bit less than that, then actually you can prove something more.
You don't allow complete graphs by disallowing, even having just a few triangles.
Right, so well, you count then how many triangles you have in this case, and then if you have much less, let's say no triangle in the extreme case, yes, because in this complete graph a lot of triangles you have, then the largest independent set is n over d times log d, and this is exact. So you can gain a little bit, but log d, and it was important to gain this log d, and even we could improve it then if you have a graph where the number of triangles is smaller than in this example, then it's more than n over d. It's n over d times some multiplied by something which tends to infinity and tends to the infinity.
So what is semi-random?
So the randomly you half, so you just choose half of the points. That is, and then in the 1/2 you find an independent set, which is of n over d. But in the another half, so if you choose it randomly, then the another half, all the properties will be maintained, so the right degree. Then you choose against the half randomly.
The degree goes down, and
yes, but in a nice way. So because you choose it randomly. But once you have a random round, then in the graph, then you by hand you choose the largest independent set that is not random, and then again half it randomly, and then choose an independent set, and of course put it together, then you will get a bigger independent set. So that is a mixture of randomness and deterministic random argument and determinist argument. So that is why we called it pseudo-random method.